Section 3.4, derivatives of trig functions. So in this section, we're going to look at the derivative of all 6 of the trig functions, try and come up with formulas for those. In order to prove those, we need some limits known involving sine and cosine. So we're going to start off looking at those, and then we'll move over to the derivative formulas for the trig functions. So in Chapter 2, we already played around with one of the limits we need, which is the limit as x approaches 0 of sine x over x. And through tables in the TI-84, we ended up estimating that that limit was 1. That is something that's only true in radian measure. If you try to do that in degree measure, you can play around with that on your calculator, you'll see you don't get a 1. So when we do calculus with trig functions, we need to always be doing that calculus in radian measure if we want the formulas we learned in this section to hold. So we only estimated that in Chapter 2. If you're interested in the proof, that is available in Section 3.4 of the text, so you can have a look at that, ask me questions about it if you're curious or confused. And let's go ahead and move on to the other limit that we need in this section. Let's look at the limit as x approaches 0 of cosine of x minus 1 over x. And we're going to do that this time just using the TI-84. The reason we're looking at these two limits, the sine x over x and this cosine x minus 1 over x, is they help us prove the formulas for derivative of sine and cosine. So we want to have a solid foundation for those first two trig functions. Once we have those, we'll be able to easily work out formulas for the rest. So we'll see that coming. For now, we're going to experiment around with these limits. So the limit as x approaches 0 of cosine of x minus 1 over x, and we're just using the TI. So we're just going to look at graphing that, and can that graph lead us to an answer. So let's switch over to the graphing calculator. Let's go into the y equals, and let's put that function in. So our numerator is cosine of x and minus 1. So I put parentheses around the numerator, and there's a parenthesis around the x also on the calculator, so make sure you close that so that your second parenthesis is closing the numerator, and then we're dividing by x. Just looking at the formula and thinking about direct substitution, if you tried to plug 0 in, cosine of 0 is 1, so you get 1 minus 1, or 0 in the numerator, and then you plug a 0 in the bottom, you get a 0. So you're getting 0 over 0. So direct substitution doesn't work, which is why we're going to look at the graph instead. And basically, you should get your estimate right away when you look at this graph. So the question is, what does it look like is happening as we approach 0 from the left and from the right with our x value? What is happening with the y value? And it sure looks like the graph goes through the point 0, 0. So right away, my estimate is that the limit is 0. And notice, though, direct substitution, we talked about this already. If you put a 0 in for x and then press enter, for the y value, it says it's not a number because it is a 0 over 0 situation. But when you trace it, it definitely looks like as you're getting closer from the left, like the y value is going to 0, and as you come in from the left over here, looks like the y value is approaching 0, and as you come in from the right, it also looks like it's approaching 0. If we want to see that a little better, we can zoom in quite a bit, and now we're estimating with closer to 0 values. But again, we see as we come in from the right, and the x value is getting closer to 0, the y value is also getting closer to 0 as we come in from the left. We see the same thing happening. So we would estimate that the overall limit of the fraction is equal to 0. So let's go ahead and head back to the notes and fill that in. So we're going to put equals 0 here. One of the things we do want to keep in mind is when you find it using the TI-84, you're just estimating it. But it does turn out there's a geometric proof that we could look at in the textbook as well that does end up saying that that is equal to 0, not just as a guess, but more as a solid proof. All right, so we're going to play around with these two limits a little bit, evaluate a couple things with them, and then we'll move on to get our formulas for the derivative of trig functions. So the first example we want to look at is, let's find the limit as x approaches 0 of sine of 2x over the sine of 5x. So we want to use one or both of these new theorems that we got, and since this one has sine only in it, we'll probably use this first one. And the key thing to using that one is that we need the same thing on both the top and the bottom. So this x and that x have to match up. So you have sine of something, and then you have that same something in the denominator without the sign. So this one's a little tricky because we don't have that or something. So what we're going to do is change this to the limit as x approaches 0. And we're going to write sine of 2x here, and no denominator at first. And we're going to move the denominator over here and write sine of 5x over on this side. All right, so now what are we going to do from there? Well, again, this idea, whatever is on the inside right here, in order for this formula to work, you need the same thing on the bottom. So what I'm going to do is insert a 2x right there so that this matches the formula where the angle inside is the same as the denominator. To balance that off, over here on the side, I'm going to make an extra fraction, and I'm going to put a 2x there so that these two x's cancel and we would get back to where we started. Except for we don't want to get back to where we started, so I'm going to leave them in there. But I'm showing you the cancellation to show you I'm not changing the value, but just the look. And then I want to do the same thing on this other one. I want the angle inside right here to match what's up here. So since we have a 5x inside the sign, I'm going to write a 5x here. And then to balance that out, since that 5x got inserted in the numerator, I'll put a 5x here so that, again, if we were to cancel, those cancel each other out. So even though I added a new thing in, it's basically just a multiplier of 1, so it's not changing any values. And then from there, we want to go ahead and go back to our derivative work and hopefully make some progress now here. So we're going to break this into 3 limits. The limit as x approaches 0 of sine of 2x over 2x. And then we're going to look at the limit as x approaches 0 of 5x over sine of 5x. And then the limit as x approaches 0 of 2x over 5x. All right, so for the first one, the limit as x approaches 0 of sine 2x over 2x, as long as you have matching portions here and here, and they're both going to 0, then according to the limit up above, that's going to be a 1 for the overall fraction. Now granted, out front it just says x is going to 0, but if x is going to 0, so is 2x. So for that first piece, we get a 1 times, how about the second piece? Well, we have the same thing going on where these two pieces match and they're going to 0. The only thing that's an issue is this is a reciprocal of the format that's up above, which means the limit we get would be the reciprocal of up above. But the above limit is a 1, and if you take the reciprocal, it's still a 1. So it turns out that that theorem for the first one holds whether you have it the way it's written or you flip it upside down. It doesn't matter. So we get a 1 for the second limit. And then for the third limit, we have some cancellation. The x's cancel, and then we just have the constant 2/5. So when we take the limit of that one, we just get 2/5. So we end up with 1 times 1 times 2/5, or just a final answer of 2/5. All right, let's go ahead and try another one. So in this one, we want to find the limit as theta goes to 0 of cosine squared of theta minus 1 over theta. So for this one, since it has the cosine in it, we're probably going to end up trying to use this formula over here. So we'd like the numerator to be cosine of x minus 1 over x. So let's see if we can make that happen down here. Obviously, we have a different variable, but the same idea. We'd like it to be cosine theta minus 1 over theta. So we have the limit as theta approaches 0, and the key thing on the numerator is we actually have an a squared minus b squared look here, because we have cosine squared minus 1 squared. So we should be able to factor that as a difference of squares, and a minus b times a plus b. So the a minus b portion would be cosine of theta minus 1, and the a plus b portion would be cosine of theta plus 1. And then we would divide all of that by theta. And now we're getting closer to what we want because we have the cosine of theta minus 1 over theta. So we know that limit from the box up above. So we just want to break that off into its own limit. So we'll look at the limit as theta goes to 0 of cosine theta minus 1 over theta times the limit as theta goes to 0 of cosine of theta plus 1. All right, so for the first one, based on up above, we see that one should be a 0. So we'll fill that one in. And then for the second one, we can just use direct substitution. So we'd get the cosine of 0, cosine of 0, plugging 0 in for theta, plus 1. So we end up with 0 times the cosine of 0, which is 1, plus 1, which is 0 times 2, which is just overall a 0. All right, we're going to move on now to the formulas for the derivative of sine and cosine. The proofs are in the book, and you can look at those if you're interested and see me if you get confused. One of the nice things about looking at those proofs in the text is you'll see those limits that we just worked with on the previous page get used to prove the derivative formulas for sine and cosine. Turns out, though, the formulas themselves, the answers to them are very nice, very simple. So the derivative with respect to x of sine of x just turns out to be cosine of x. And the derivative with respect to x of cosine of x just turns out to be the negative of the sine of x. So kind of is almost as simple as you could hope for. If it wasn't that negative sign on the second one, then this would be as simple as can be. So derivative of sine is cosine. Derivative of cosine is negative sine. Again, proofs of those in the text using the limits from the previous page. So let's take those for granted as truths, and let's use those to come up with the formulas for a couple of the other ones. So let's try and figure out what's the derivative of tangent of x. So we're going to try and come up with a formula for the derivative with respect to x of tangent of x. And a little bit of a spoiler there. They told us how it's going to get done. We're going to use the quotient rule. Seems a little strange to say we're going to use the quotient rule when there's no division, but remember, tangent is in fact a division. Tangent is sine of x over cosine of x. So there's where the division comes in. So now we're going to want to apply the quotient rule to that. So we want to take the derivative of the numerator. So the derivative of sine is cosine of x times the denominator left alone minus the numerator left alone times the derivative of the denominator. And the derivative of cosine x is negative sine x. And then all of that would be over the denominator squared, which would be cosine of x squared or cosine squared of x, writing that with the shorthand. So just kind of showing you the quotient rule in action. Here was our numerator, and we took the derivative of that numerator, and then we left that alone over here. And then here was our denominator, which got left alone in the first part of the quotient rule, but we took its derivative in the second piece, and we squared it in the denominator. All right, so let's simplify that now. So we have up top a cosine squared x, and two negatives make a positive, and we get sine squared x, and all of that is over cosine squared x. So one of your trig identities that you'd want to remember is cosine squared x plus sine squared x is equal to 1. So using that identity, I can replace the numerator with a 1, and I just have cosine squared x in the denominator. So I have 1 over cosine of x squared, but 1 over cosine is secant, so that's secant of x squared or secant squared x. So what is the derivative of tangent of x? The derivative of tangent of x is secant squared of x. So that one we were able to prove ourselves. We didn't have to use anything overly complicated or geometry like they do for sine or cosine, because Tangent is the quotient of sine and cosine, so if we know those two, which we do from up here, we know the derivative of sine and cosine, we can just use those to get the derivative of tangent. So let's go ahead and try that one more time with a derivative of cosecant. So we're trying to find the derivative with respect to x of cosecant of x, which is the same thing as saying 1 over sine of x is equal to cosecant of x. And instead of the d dx notation, I'll just use the prime. So we want the derivative of that. So to take that derivative, we actually have to use the quotient rule again because it's 1 over. So we still have a fraction here. And the numerator of our fraction is the 1. Denominator of the fraction is the sine of x. So we're going to think about those as we do the quotient rule. So we do the derivative of the numerator, which is 0, derivative of 1 is 0, times the denominator left alone, so sine x, always a subtraction in the quotient rule. And then we're going to take the numerator and leave it alone, times the derivative of the denominator, and derivative of sine x is cosine of x. And then we're going to have all of that over the denominator squared, so that would be sine squared of x. All right, so the 0 makes that piece go away, and we just end up with negative cosine of x over sine squared of x. And that is the derivative, but that's not the way that we normally hear that or have it expressed. So let me show you where the other way that we express it does come from. So we have a negative out front, and then we have cosine of x over sine of x, and then that's times 1 over sine x. So I just took the sine x in the denominator and split it into two pieces. And then cosine over sine, so sine over cosine is tangent, so negative cosine over sine is cotangent. And then 1 over sine is cosecant. And usually they write that in the opposite order, so let me just switch that around. Negative cosecant x, cotangent x. So another derivative formula proven for us. So the derivative of cosecant of x is equal to the negative of cosecant of x times the cotangent of x. So there's two of them proven. There's two that we didn't do. You could do those on your own. It's possible you might see them as homework exercises as well. But let's go ahead and make one table here to summarize all of these derivatives. And again, keep in mind that these only work if you're in radian measure. So when we do calculus, we're going to always try and make sure that we're working in radian measure so we have simple derivative formulas. It's possible to do derivatives in degrees, but then the formulas aren't as simple as they are here. So here's our summary, and we will want to memorize everything from this chart. So first of all, the derivative of sine of x, cosine of x. Derivative of cosine, negative sine. Derivative of tangent of x is secant squared. And the derivative of cosecant, we already have that one filled up in from right above. That one would be negative cosecant x, cotangent x. And then the two we didn't prove, I'll fill in for you. The derivative of secant x is secant x, tangent x. And the derivative of cotangent x is negative cosecant squared of x. So there's all 6 of your trig functions, derivative formulas, and just like I mentioned to you with the product and quotient rule, these are things we're going to need to memorize. It's not going to be a good thing if every time you get one of these you have to go look it up. So make sure that instead of looking it up, you're committing those to memory so that you can do them quickly when needed. All right, let's go ahead and look at some examples that use those formulas we just developed. Let's find the derivative of y with respect to x for each of the following functions. The first one is h of x, which is equal to 2 sine of x cotangent of x. Now when you look at that initially, what you should be thinking is that you're going to end up using the product rule, because you have 2 sine x as one function, cotangent of x is the other one, so it looks like there's a product here. There is a product here, but it turns out that because cotangent is a function that's defined in terms of sines and cosines, we can simplify this a bit before we get started and make this easier. So let's go ahead and just work on h of x a little bit before we try and take a derivative. So I'm going to copy the 2 sine x, and then cotangent is cosine over sine. So let's put this over 1, and then cotangent of x is cosine of x over sine of x. And what's nice about that is these sine of x's can cancel, and that just leaves us with 2 cosine of x. So now we can take the derivative without having to use the product rule. There is a product here because we have 2 times cosine, but remember we have the constant rule, which says that constants can just be factored out front, and then you can just take the derivative of the other piece. The other piece in this case being the cosine function, which has a derivative of negative of sine x. And then the negative we can factor out front, and we get negative 2 times the sine of x. And that is the answer, but there's also an interesting little catch to this one as well, which is in the original function, we had sine of x in the denominator. And so that means there's times where the original function is undefined, and that would be anywhere that sine of x was equal to 0. So if we thought about the unit circle, sine is the y-coordinate on the unit circle, and the y-coordinate is 0 here and here, which would be at 0, pi, 2 pi, 3 pi, 4 pi, and so on. So this is the derivative, except when x is equal to an integer times pi. And it's interesting because in the final answer right here, those numbers that we just talked about as being a problem, they don't actually make that answer undefined. But because they make the original function undefined, it's not possible for a function to have a derivative where the original function was undefined. So we end up, because of some holes in the function, having to put some exceptions on our derivative. All right, let's go ahead and look at another one. F of x equals cosine of pi over 6. This looks like one where you're going to use the derivative of cosine as negative sine, but it turns out that that's not true, because cosine of pi over 6, let's think about that. Cosine of pi over 6 is the x-coordinate right here, which would be root 3 over 2 for the x-coordinate. So this is the same as saying f of x equals root 3 over 2. In either case, whether you're thinking about it as cosine of pi over x, or if you're thinking of it as root 3 over 2, either way it's a constant, and the derivative of a constant is 0. So we end up actually not using our formulas for derivatives of trig functions here, because we're actually just dealing with a constant. So be aware of some tricky options like that. Let's go ahead and look at another one. F of x is equal to x squared times cosine of x. All right, this time we've got a product. We've got x squared, and we've got cosine of x. We've got 2 functions multiplied together, and we can't make that product go away. We can't carry out the multiplication. We can't cancel anything. So we're just stuck with the fact that it's a product, and that means we're stuck with using the product rule. So to use the product rule, we take the derivative of the first factor, which would be 2x, times the second factor left alone, plus the first factor left alone times the derivative of the second factor, and derivative of cosine is negative sine x. So going back, the cosine x from the second factor is left alone the first time, derivative second time. The x squared derivative the first time, left alone the second time. And then in terms of simplifying, we could probably simplify a little bit. We could factor an x out front, and that would leave us with 2 cosine of x. We could move the negative out front on this one, so negative x sine x. I think that's about as much as we can do with that. So there's the simplified and factored version of that derivative. So we had to use a product rule there, no avoiding it. And in a similar vein, here's one where we have a quotient. And we probably could do some manipulating around with the secant and the tangent to get that in terms of sines and cosines, but I don't think that all that manipulation would end up making this not be a quotient rule. So we're stuck doing the quotient rule here, so let's think about the pieces. For our numerator, we have 1 minus secant x. For our denominator, we have tangent. So as we apply the quotient rule, we'll have to think about those pieces. So for f prime of x, we want to take the derivative of the numerator. Derivative of 1 is 0. Derivative, we'll copy the negative, and then the derivative of secant is secant x, tangent x, and then we'll copy the tangent x for the second piece. So just to kind of highlight that for you, there's our derivative of the numerator. This piece is just us copying the denominator. And then minus, copy the numerator, 1 minus secant x, times the derivative of tangent, which I'll squeeze in here, is secant squared x. So again, just following the pieces, the numerator is left alone, so 1 minus secant x, and the denominator, we take the derivative, and the derivative of tangent is secant squared. And then all of that is over the denominator squared, which would be tangent squared of x. And we can highlight that in green, I suppose, just so everything is color-coded. And that is your derivative. We could do a little bit of simplifying, so we'll go ahead and work on that some. The two tangents in the numerator, we could combine those. So that would be a tan squared. And then on the other one, I don't know. There is some simplification we could do, but I think I'd probably just leave it as is. And I think I'm going to go ahead and stop simplifying too as soon as we get this step written down. I do see a little bit more that we could do, but again, as I mentioned before, if your directions are just to find the derivative, then you don't always have to simplify as far as possible. And, if you needed to graph the derivative or find the derivative at the value of, pi over 3 or something, we could plug in and we could find that. I will just point out one bit I see that we could definitely move forward a little bit more, as there's a secant in this factor, and in the in this first term, there's a secant, and in this second term, there's also a secant. So you could factor a secant out front, but it doesn't cancel with anything in the bottom, so I don't know that I would go any further. So I think I would just take this piece and say, there's my derivative. And again, we had to apply the quotient rule, couldn't really get around that. All right, let's go ahead and look at a couple more examples. In part E, we have f of x equal to x times sine of x over 1 plus cosine of x. Still with the same directions from the previous page, which is to find the derivative. So this one's interesting because we have a couple things going on. We've got a numerator, x sine x, and then we've got a denominator, 1 plus cosine x. So we're going to use the quotient rule because that's all being held together by division. And in fact, we'll use the quotient rule first. But the other thing that is of note is we've also got a product in the numerator too, because it says x times sine of x. So at some point, the product rule is going to have to get involved too. So let's go ahead and take a look at this. For f prime of x, we're going to start off using the quotient rule. So I want the derivative of the numerator, and bang, right there, that's where the product rule comes in. So I'm just going to write that. We need the derivative of the numerator. So the numerator is x sine x, and we need the derivative of that. I'm not just carrying it out right there because it's a product rule, so I'm going to slow down and break that into pieces. But we need the derivative of the numerator times the denominator left alone, so 1 plus cosine x. And then for the quotient rule, we want to subtract the numerator left alone times the derivative of the denominator. And that one I could take, but since we have to work on the other piece in a minute, I'll just write this with the prime notation as well. So we want the derivative of the denominator there, and then all of that is going to be over the denominator squared. Keep in mind, by the way, with the 1 plus cosine x squared, I didn't write 1 squared plus cosine squared x because you can't distribute a square when there is an addition or subtraction. All right, so now let's keep going on this. Actually, let's do the color coding. So our denominator was the 1 plus cosine x that got left alone in the first term. We're going to take its derivative in the second term, but we didn't do that yet. We just marked it for that, and then we need that denominator to be squared in the new denominator of the derivative. The numerator, which was the x sine x, we're going to need to take its derivative here, but we've only marked it for that with the prime. We haven't done it yet, and then we left it alone over here. All right, so let's get to work on that now. So when we go to do the next step, for the derivative of this x sine x, that is a product. There's multiplication right there. So we have to use the product rule. So I'm going to keep that in brackets. Derivative of the first factor, the x is a 1, times sine x left alone, plus x left alone times the derivative of sine of x, which is cosine of x. So all of that is just the derivative of the numerator, and it's messy like this because the numerator had a product. And then that is going to be times 1 plus cosine of x. I'm not taking a derivative there because that piece gets left alone. Same thing with the x sine x over here. But we do still have the prime on this, so we need to take that derivative. So the derivative of the 1 is 0, and the derivative of cosine is negative sine. So let me get rid of that plus, make that a negative, and then all of that is over 1 plus cosine of x squared. And that is our derivative. It is not simplified, even kind of, but that is the derivative. So let's just simplify it a tiny bit, and then we're going to stop on this one. So a little bit of simplification, things like the 1 times sine x is just sine x. And then we have plus x cosine x. That's times 1 plus cosine x. And then over here, this piece right here is just negative sine x. So those two negatives right there are going to make a positive. And then the x is out front, and then we have sine x times sine x would be sine squared x. And then all of that is over 1 plus cosine of x squared. And I think I'm going to go ahead and stop right there and just highlight that as our answer. Could it be simplified some more? Possibly, but we've done the obvious easy simplification, and again, that is the derivative. So if we needed the derivative to find a slope or something like that, we've got it. So I think we're fine right there, and my open math should take an answer in that form. Before we move on, I will just point out there is a simplification that is tempting that doesn't work. People often would want to cancel this 1 plus cosine x with one of the 1 plus cosine x's down in the bottom. You can't do that because of this addition right here, means that the 1 plus cosine x in the numerator is not a factor of the entire numerator and therefore can't be canceled. So that's always tempting because you have that copy of the denominator left alone in the first part of the quotient rule and then the denominator squared, but because of the plus sign, you can't do the cancellation there. All right, let's move on to the last one. Find the equation of the tangent line to y equals cosecant of x at pi over 4. All right, so if you want to find the equation of a tangent line, then you need its slope, and the slope comes from the derivative of the function. The derivative of cosecant is negative cosecant x tangent x. And then if I want to get the actual slope of the tangent line, I need to plug in. So m tangent, so the slope of the tangent is equal to the derivative with pi over 4 plugged into it. So negative cosecant of pi over 4 times the tangent of pi over 4. So one of my weaknesses in trig is I don't have my trig functions memorized for cosecant and cotangent, I like to just change those to the functions that I know better. So cosecant is 1 over sine. So I'm going to write this as negative tangent of pi over 4. And then that cosecant is 1 over sine, so I'll move that sine of pi over 4 down here. And then if you think about this one on the unit circle, pi over 4 is the 45-degree angle right there, which on the unit circle has root 2 over 2, root 2 over 2 as its coordinates. So that means both the sine and the cosine are root 2 over 2. And then tangent, which is sine over cosine, since those two are the same, would be a 1. So we have a negative out front. Tangent of pi over 4 is a root 2 over 2 over itself. So that's a 1. And in the bottom, we would have root 2 over 2, which, if you do the 1 over as a reciprocal, so that would be negative 2 over root 2. We can rationalize that as well. And we'll get negative 2 root 2 over 2. The 2's cancel, and we end up with just negative of root 2. That's our slope for our tangent line. So the next thing that we need, if we're going to try and come up with the equation of the tangent line, is the y value. So if x is equal to pi over 4, that implies y would come from plugging pi over 4 into the original function. So into cosecant of pi over 4, which 1 over sine over pi over 4, like we talked about above. So that's 1 over root 2 over 2. And we just did the simplification of 1 over root 2 over 2, and it ends up being root 2. So now we know our y value. And if you wanted to, you could say that's the y0, and this is the x0 in terms of the point slope formula. So our tangent line would be y minus the y coordinate, so y minus root 2, equals our slope, which was negative root 2, times x minus the x coordinate we're talking about, which is pi over 4. And I think that's fine as an equation of the tangent line. If you need to graph it, we could move the root 2 to the other side. So we could take this piece right here and add that to both sides. So I'll go ahead and do that so we can look at it in the graphing calculator. So we'd get y equals negative root 2 times x minus pi over 4. And then we're moving that over, so that would be a plus root 2. So I'm going to say there's my equation of my tangent line. There's my answer to the overall question. It is this piece right here. Now, just a quick mention about entering that in on the computer. If they ask you for the equation, you should be able to type it in just like this. But if they happen to ask you what's the slope, then that would be negative root 2 over 2. If they ask you what's the y-intercept, that would be combining this term and that term. So you would have to clear parentheses and combine your constants up to think about what the b is in y equals mx plus b. All right, it's just one final step on this one. I do want to graph the original function along with this tangent line and see if it really looks like a tangent line. When you have messy work like this, the reason they ask you in the homework sometime to graph it is just to see, does it look like a tangent? And if it doesn't, you know something went wrong. So let's go over to the graphing calculator and we'll enter in a couple things. So the first one's just the original function. So y is equal to, actually, you know what, before I enter in the original function, let me just show you one other thing. Next to the second key is the mode key. Make sure you're in radian mode. So that's degree mode, that's radian mode. Down there in the second section, kind of middle lower there, degree, radian. So I want to make sure I'm in radian mode, otherwise this isn't going to work out. All right, so now entering the two functions. The original function they gave us was cosecant of x. That's not on the keypad, so I'm going to say that is 1 divided by the sine of x. Whoops. 1 divided by the sine of x. So 1 over sine is cosecant, so I'm going to have to graph that way. I think if you dig in there somewhere, you can find the cosecants, but I just would use the other version of it. What is cosecant? It's 1 over sine. All right, and then we want to graph our tangent line. So that is negative square root of 2. Looks like the negative didn't take, so let me do that again. Negative square root of 2. And then times parentheses x minus pi over 4. Above the division key in orange, you can see the pi key. So I'm hitting the orange second key and then pi divided by 4. I suppose you could put in 3.14 as an estimate, but better to use the pi key on your graphing calculator to get a lot more decimal places of accuracy. And then plus root 2, so second square root and 2. So we've got the original function, cosecant, written as the 1 over sine. And then we've got our negative root times x minus pi over 4 plus the root 2 from the other side. So I'm going to go to the graphing page. We want to look at this at pi over 4. So let's see. Pi over 4. There we go. Certainly I'm seeing a tangent line there. Pi is 3.14. Let's just say it was 3. 3 divided by 4 is 0.75. So pi divided by 4 would be a little bigger than 0.75. So let's see where the point of tangency is. Looks like somewhere right around there. 0.8, 0.7 something. So that seems right to me. It should actually lock in as an intersection. Those two do touch, but for some reason it's not catching that. But notice that when the two come together there, it really looks like we've got a tangent line. So that's a good check on our work. All right, that wraps up section 3.4.